Sure, to this computer. All right. Welcome back, everyone. So restarting the distributed systems reading group. The platform that we use to schedule these, Luma, changed how they manage recurring events. So instead of being now like a recurring series, a meeting series, now it's as part of a quote calendar, which means we lost the entire mailing list, which sucks. So we're gonna have to sign everybody back up again. I think I have the option to go back because we still have the mailing list from the previous one, and I can just email everybody, but that also feels kind of like a crappy thing to do, email several hundred people. So we're just basically going to rebuild this thing from scratch, I think. So this month, to kick things back off, I've selected Beehive, which is a paper I've had rattling around in the background for a little bit, especially given some of the work that my previous company was doing with IPFS. And I always thought that this might be an interesting way to handle some of the performance challenges that you could sometimes see on that network. Yeah, without further ado, does anybody want to give a summary of the paper or like a high level sketch of what this is all about? Maybe Brent?
I can give a one sentence response.
Sure.
So lookups as is are really bad. They're like order login, but you can get them to order one if you start distributing data and replicating it. Now, the devil's in the details, and there's a lot more. Other people, please expound. I'm sorry, maybe that wasn't very good.
I mean, that's definitely a good start. Anyone else? Like there's just four of us, right? So I can I'll always hop in as the backstop here if needed. But James, do you want to give it a go?
Oh, I got called out. Yeah, I think
there's four of us, right?
I had a 50-50 chance though.
Yeah.
So yes, so the high level gist is to go from order login to constant time lookups in DHTs. The method, if I understand it, for doing that is basically to push the most frequently accessed records to closest peers, right? Um, so in a DHT, I only really know Kademlia because IPFS, but I gather most DHTs work similarly, where you have a prefix, and so your nearest one will be basically your current prefix minus one. And so so you have to track for your like home node content, you have to track how frequently your content's being queried, and then at a given interval you push the most common ones to your closest peers, and eventually that means that you end up with constant time lookup because the most commonly requested things are as close to the requester as possible.
Yeah, exactly. So the main insights, I think, if I look at my notes, should I make these notes public? I don't know. Well, actually, they are published to my Obsidian. So,
Oh,
but the core insights are, latency is a killer in distributed systems. Not to say anything even about availability, right? But just latency. And while we have lots and lots of headroom still for bandwidth, latency is bounded by the speed of light, right? So if you're doing lots of back and forths or lots of hops, that's going to kill your performance. And all of the major DHTs that we have today work basically on this principle that James described. And the two things that they do, or that they suggest, is if we assume that content popularity follows a power law. So can I annotate directly on here? I think so.
But did you give up
No.
on GoodNotes?
No, I still use GoodNotes, but I didn't want to have all my annotations on the video. So,
Fair enough.
so yeah, so we have this, and power law looks something like that. So if this axis, y-axis, is popularity, and this is frequency. Right? So you'll have a very small number of items that are very, very popular, and then a long tail of less popular things that very few people are looking for. And so one strategy for speeding up the entire network is to say, hey, what if we made it really easy to get the popular data, right? Made that really fast. Then with a small amount of effort, we can make a huge difference, right? So if you think about front page of Hacker News content, right? So everybody gets swarmed if they hit the front page of Hacker News and then their site goes down. Well, that's no good, right? And that stuff should be really, really fast because it should be widely cached. Lots of people should have copies of this because they're already downloading it to look at it, right?
Or as the paper references, getting slash dotted, which certainly dated the paper. Yeah.
Yes, it did. Right, yeah. So that's that's insight one. And insight two is that we can do this just with knowledge of yourself and your neighbors. So one of the notes that I took, and we haven't looked at in this group previously, eigentrust, but this reminded me a lot of, and then I will shut up and we can discuss the paper, but reminded me a lot of eigentrust, which is one of the most widely cited distributed systems papers, which is about how do you transitively trust, like if I trust Brent, and Brent like to 90%, and Brent trusts James 40%, right? It's like, yeah, I know you a little bit, but I don't know you that well. How much should I then trust James, right? And it follows the same pattern where you're just looking at your local trust and then hearing from, or affecting things with your neighbors and sharing these lists around. And so it's the same thing where we don't have to globally agree on what popular content is. I just have to say, for me, this is popular. So I'm going to push it to my neighbors, and that should coalesce at the macro scale for everyone, which means I think, and I would actually like to talk about drawbacks later, I think that actually solves for a lot of Byzantine conditions as well, which is kind of nice. So yeah, so they looked at these, performance, scalability, adaptivity. They wanted it to be updatable live, so to tweak these parameters live without having to take the whole system down and bring it back up. They did a DNS implementation on top of Pastry with really impressive results, which is always nice.
I felt a little trolled by that. Yeah.
Oh, did you? Oh, no. Tell me more. Why? Because you were our DNS jockey at Fission. Yeah.
DNS champion at Fission. Yeah.
Yeah. Side note, seeing that pattern getting used more and more recently. So I just got back from Jay on the Beach in Spain, and Number Zero gave a talk there about the latest stuff that they're working on with IRO. And they're also using DNS as a distribution mechanism, text records, for finding at minimum handshake servers. And I think maybe for some routing things as well. So you can always drop back into, they have a distributed DNS thing, basically, PAKRR, I think. But then they also push into DNS. Using DNS as a distributed key value store, which it is both a good idea, I think, from real world usage. Like, James, would you agree or disagree? I don't know. You're the one who actually have to deal with this stuff. Yeah.
Yeah, agree.
Yeah. And Quinn and I ran into one of the creators of DNS 2 years ago or so, and we mentioned that we were using this one. He's like, yes, that is in fact how it's supposed to be done. So yeah. So and anyway, back to this. So yeah, it's like these graphs were really impressive. I thought, how much better they did, and especially relative to caching, right? Which is what, for example, IPFS depends a lot on caching for this use case, right? It's like if your node gets asked for something, then you have a copy of it around, temporarily at least, right? And so doing this proactive replication can really, really help. I found the implementation and the analysis that they had, the empirical analysis of this, really interesting, and it felt a little bit like they might be cheating on tuning certain parameters. But I'd love to hear what other people thought about the paper overall. Like, does this seem plausible? Does it? Are there concerns you have? Opening up the floor. I'll stop talking now, basically.
I have questions, I guess for what people think. So one of the things that they address specifically with, one of the vulnerabilities for DNS in its current hierarchical system is it puts the root nodes, or the highest level nodes, makes them vulnerable, right, to DDoS and things, right? Like they're a target, because if you can mess with them, you can mess with the whole system. What I didn't get from this, so I understand how this can speed up the lookups, but the authority, as far as, like, in my reading, like the authority for records, particularly they talk about like mutable records, right? The authority for that still lies in the home node, right? So if you take out the home node, or like you were mentioning Byzantine stuff, like if the home node just goes offline, like you have what's been replicated, but you end up, it seemed to me like you end up in a system where you have no idea if this is actually still valid, right? Like they mention adding version numbers, but you have no way to know. In fact, it's on the screen there, the version ID. You can compare if you have a newer version ID, but you have no idea where you are in the version set. So I don't know. It wasn't clear to me, other than having it a little less clear where the home nodes are potentially for an attacker. Like, it doesn't seem to get around that, as far as I could tell. But I guess pretend there's a question mark at the end of that. Is that a correct reading?
Anyone want to share thoughts on that? All right, cool. It'll be me. So yeah, I think that's a totally valid.
Oh, may I just ask
please.
a question?
Yeah.
Okay. One concern regarding Brett's question, I think the paper is mostly concerned with, the distributed side of stuff, and not the security stuff. That's just my opinion. I have to read it a couple of times, but this question is a valid question, but it's a very different subject. That's it. That's just my very simple opinion. Sorry.
Yeah. So in distributed systems, we often do worry about the security side, right? Like, is a certain protocol Byzantine fault tolerant, right? It is a distributed systems question often, right? It's why blockchains exist, for example, right? Is that they're Byzantine fault tolerant network, highly secure, with trade-offs, right? They're very slow, but you're guaranteed to have like the latest information, because we're making sure that we're synchronously updating, from time to time on a regular schedule. And there are lots of networks that just assume trust, right? And so I agree. I think that they don't. One of my concerns with this paper is that they don't really think too much about the Byzantine case. This is very much in a friendly, non-adversarial situation, right? It's like, oh yeah, no, I'm totally going to replicate that for you. I'm not lying, right?
Right. Yeah.
Or they mentioned somewhere in here, there's we should probably extend this to also include like how big that file is, right? Because if it's like a petabyte of data, we're just going to fill your disk.
yeah, we could just start
Yeah.
sending you all kinds of bogus replication information, and good luck.
Yeah. Or Sybil attack the network, right? So it's like, okay, so even when you have these just local nodes and they're replicating out, that kind of lowers the blast radius, assuming that most of the network is honest, right? But if you fill it with nodes that are malicious, then they can start pushing data around to everybody. They can completely blow that table. So I made a allusion earlier to, or analogy earlier to eigentrust. There's a bunch of papers that came out of that series of work, one of which, maybe we should actually look at eigentrust plus, which tries to solve for the Byzantine node problem. Like, what if we just have a bunch of Byzantine nodes that are lying to everybody and blowing the curve, and handling really specific edge cases in it? So yeah, absolutely, right.
Yeah.
This mutable file portion, I've made notes in my notes of like, okay, it's interesting that they're really worried about mutability. They're obviously thinking about a certain use case. This paper was written in 2004. Replicated data types already existed, like as a class of thing, but not CRDTs yet. And so if we think about this from, I these days think a lot about, local per software, things like this. It's like, okay, they're coming at this from what's the document ID and like the almost like a Lamport clock, like what's the version number on it going forward versus what's this particular piece of data? Like, they're not dealing in CIDs. This isn't static data. This is mutable data. Is there a way that we could reframe this? And I don't have an answer to this right now, but is there a way that we could reframe this as not trying to push version records around, handle the mutable pointer with some other mechanism, or even make that a smaller part of the system, and then only deal in blocks with hashes, and like don't worry about this problem for the most part? I think would be interesting way of handling it. But yeah, it did stand out to me that they were using specifically mutable version numbers.
Right.
Yeah. And sorry, James, because we went on a bit of a tangent there. Your original question about version IDs was, if you can get eclipsed, basically, or like have your latest record DOSed.
Right.
So this is a problem that we see a lot in like pub subsystems like this. It's really, really difficult to prevent your network from being censoring updates, right? So if you think about a graph, that's so these are all different nodes, and it has it's really hard to. So it's never mind. I'm not going to try to draw. It has some series of connections, and you're gossiping messages between them. Then you can end up in this, again, especially if you have malicious nodes, you can end up in this little island where you can't push updates out. So there's a trade-off here, right? Is if you hit a TTL and then it fails, is the record unset, or is it good enough to have old data? And I think that depends on the consistency of your domain, right? May Milano gave this really great talk at Strange Loop, and I think she actually just gave it at Codebeam as well, about how you can even have like flexible consistency levels and say like, well, in this program, these variables require eventual consistency, and then this one down here has to be like in an absolute lockstep, and they can even mix and match those in a particular application. If you have eventually consistent data, you have a CRDT, well, the old record is still valid. You're just delayed in hearing about the new stuff, and that's okay. But if you have the example she gives is if you have a leaderboard, in an online video game, that had better be up to date, right?
Yeah.
So yeah, it depends. In gossip networks, broadly, epidemic broadcast. As long as you have at least one trusted node that you can talk through and get out of that island, then you're okay. Then the message will propagate out. But that really depends on, so as you said, who's the source of truth? And does that have to be a location, or can we make that the message itself? Can I sign that with my public key and then disseminate that? And you'll never know that you're up to date. In fact, you have to always assume that you're somewhat behind.
Right.
So you can't assume that you have the latest and greatest version unless you switch to a synchronous protocol where you say every 5 minutes we expire the write, and you either have nothing or an answer, right? So there's always this trade-off, which is from FLP, which we've looked at previously. Chat says, enjoying listening after a bit of insomnia. Fair. I'm extremely jet lagged currently. So just got back Sunday night from Spain, where I was jet lagged for a week and then got onto Spanish time and then immediately flew back. So I'm right there with you.
Sounds about right.
Yeah. And then in a week and a half, I go to Berlin, right? So it's like, this will be a month of jet lag. Yeah, but yeah, so it's I think it is worth noting that DNS has the same problem. And a project that Blaine had explored, Blaine Cook at one point had explored, was almost like a DNS, not alternative, because it could also include DNS, but like a higher level key value store that was the way we were talking about it, at least, was that it was eventually consistent, so that you would always have high availability on the records, but you might be out of date, and that's just something that you had to deal with. And in such a system, you can't even assume that you know when something was written, right? There are ways of doing it, but they're they're all online protocols, so you kind of there's all these trade-offs, right? It's one of the things that I'm actually sort of like itching to work on. I don't think it would be that much work to actually do. But always being able to get some record, I think, is useful. And then looking at it and being like, well, is this still a valid record? Even if it's invalid, is it good enough for my particular use case as opposed to what the author said, right? Always having to be able to dial a particular home server in DNS, which I think is a bit of a lie because everybody uses heavy caching, right?
Yeah.
I think in practice, that's what we end up seeing is people use caching for the most part.
Yeah.
Right?
I mean, I guess and maybe I got too hung up on the fact that their target use case was DNS. Because like this is more efficient than caching, right? Because it's proactive, right? It's pushing, basically it's warming your cache for you is essentially what it's doing. Based on historical access patterns. But it doesn't seem to solve, and maybe this is also like, because they listed a bunch of the downsides of DNS, and then we're like, we have an optimization for one thing, which is, I don't think is the key, because DNS is so heavily cached, right? Like your average internet experience rarely is because the DNS lookup was slow, right? Like so things don't go wrong because your DNS lookup was slow, right? It's like, it's what happens after that. And actually, one of my other questions, which is like, maybe this is too in the weeds for this, is like, this also, if we think about IPFS, right? The DHT lookup is not the slow part of IPFS, right? The DHT lookup, like, sure, could be optimized, but again, right? Like Kubo nodes already cache a bunch of that. It's the like getting the stuff after that once you've located it, right? That's where IPFS tends to fail completely or just be slow. So I guess like, like the meta thing that kept coming up for me is like, okay, but what is this really fixing, right? Like who is this for, and why would you use it? Because it adds significant overhead too, right? With all the chatting around doing you have to track a bunch more things at each node, and then you have this extra chatting around sending replication updates.
So funny you mentioned the transfer speed in a network like IPFS, because what we're looking at next month is practically rateless set reconciliation, or
I'll come
practical
back.
setless. Yeah, this paper is awesome. It's really, really fantastic. Brendan at Number Zero did a series of videos. I would say it's 3 videos. The first 2 are like background.
Oh, I
And then
remember
the
when he
third
did that. Those are in my YouTube watch later.
Oh, okay. So he
Yeah.
does a good job of explaining sort of like, I mean, they're a couple minute videos each. It's not like, in detail, but he does a good job of explaining sort of like the key insights. And we'll talk about it next month, but it was basically, at Fission, we had explored a lot of things to speed up transfer, and discovery and figuring out like, okay, what parts of this do you already have? And they have this like actually really, really, really clever solution. So I'm really excited about this paper. Everybody should come back next month. It's pretty cool. And I'm hoping that Number Zero will have add some time to play with it by then. So I'm going to see if I can rope Brendan in to come talk about it. So since you mentioned overhead and chattiness, one of the goals in the paper was to reduce chattiness of the protocol overall.
Yep.
Which they do, but you're right that it is front loaded.
Right.
So they're really chatty up front, and then they don't have to chat after. And I think that's actually in one of these latency hops, sort
I
of
think
time.
maybe the one you had initially.
These only transfers versus time. One of these has it. Storage requirements versus latency hops. Yeah, extra bandwidth overhead temporarily to replicate, and then you don't have to chat after. So Beehive is this blue line down there versus pastry.
In picking this paper for this month, like where do you see Beehive providing value, right? Like, or just that it's an interesting approach.
It's an interesting approach, I think.
Yeah. Okay.
Yeah. So there's my other motivation with this one. So like, look, am I going to write a bunch of stuff based on Beehive, next week and then like submit it to Kubo or something? Unlikely, right? But trying to share these ideas more. Something that they don't talk about in the paper that I'm interested in, and that a lot of networks, open networks like this, try to incentivize in other ways. So BitTorrent, they have their seed leach ratio, private trackers, things like this. In the IPFS world, they have I can't remember the name of the Saturn's trying to do like a CD, economically incentivized CDN, that sort of thing. But I think defaults are very powerful, and replication is because you can have a data availability problem as well. So let's say that there's a network partition in here, and you can't talk to the home node for some reason. You're kind of screwed most of the time, even if it's quote popular data, or that server may get hit with just tons and tons of requests. So if we're going to talk about this as being like commons infrastructure where we're helping each other out over time, having more copies of the data around closer to individual people just as a default. Like, let's say you put aside a gig of storage and the popular content is like images. That's a lot of images. That's a big part of that power law, right?
Mm-hmm.
And if you just build that in and say, yeah, you can turn it off, you can set this flag to false, people basically won't. So I think that might be interesting, and can also then, like, all of these networks have overhead that is basically by definition slower than a like a cloud or traditional edge system, where you're pre-deploying stuff. You're basically running this, but manually by yourself, right? You're saying, I think this is important content that a lot of people will want. And then that's, if you have a lot of money to throw at the problem, then you don't really care and you can be wasteful. If you're a little bit more cash constrained, then you actually work out how much you have to push around. For these kinds of networks to be widely used, then you need to catch up in terms of speed, right? We've seen so many projects suffer from performance, right? And you can always do this multi-tiered thing where you have like, hey, here's the open network, and then some centralized system. And if you can't get it off the centralized thing, go to the DHT, right? Cool. And that's basically what BitTorrent does with like magnet links, where often you'll have like, hey, here's the hash. You should try these servers first and just avoid the DHT entirely. And if you can't find it, then you fall back. But it would be nice for the default thing to just do it. And so I think that there is an opportunity there to just have like a small proactive cache that could not just speed things up, but also provide availability closer to users. If that makes sense. But that also might be too utopian. I don't know. So but sort of the underlying question in there is like, well, why this paper? Are we trying to do something like practical with it? This is just a reading group, right? It's like, hey, this is an interesting approach. Yeah.
Yeah, no, I definitely I like the high level approach, right? Like obviously being proactive, and they were able to identify ways to cleverly be proactive, right? In a way that's good. I get stuck on boring things like, yeah, but where would you use this?
Yeah,
right?
yeah.
Like where does it really win?
Yeah. Well, and then also they've picked a problem domain where so DNS caching, that's obviously done well, it doesn't have to be, but it's often done lazily, right? It's like, well, I requested this thing, so I'm going to go to my next layer up, grab the data, and they're doing this proactively so you can avoid those when they happen. But those are like relatively stable network with records that aren't updating very frequently. So like, oh, look at this really nice line we have here. It converges in like, I think there was like 2 rounds. Then you look at the time and you're like, wait, this is, they converge after 16 hours. That's 2 rounds because the rounds are, latency is an average, rolling average over 46 minutes, 48 minutes. And, here's 40 hours and, right. So it's like these very, very long periods of time. I'm not sure that this generalizes. I don't know one way or the other if this generalizes to a network where you have nodes entering and leaving really quickly.
Right.
And they note somewhere else that if a node disconnects and you're depending on them to, or like it's assumed that they're replicating the relevant data, the network will automatically self-heal and you'll re-replicate out. But there's delay in that, right? So it's like there's this trade-off now between chattiness and and the benefits. Since we keep talking about IPFS, there's that network analysis done years ago now, 2020 or something, where they found, again, it was a power law, right? Where most nodes were connected to the network for less than 5 minutes. They're basically leeches, if we want to use that terminology. Which is a really difficult context to work in, right? And part of the reason why I think this works so well for, say, BitTorrent is because people are downloading their, multi-gig Linux ISOs. And then, you're around for a bit, and as you're downloading, you can reprovide. But if you're pulling down a DNS record, that's tiny, and you're up and down, and you're gone. So.
May I ask a question?
Yeah.
Since this paper is for you said 2004, if I'm correct, that's like almost 20 years. And it's interesting because GFS came in, I think, 2003, and it was much more applicable and close to the ground. Are you like, can you like compare the ideas in GFS and Beehive, since Beehive is somewhat more high level? And has Beehive been applied in production systems? if you're aware of any. Thank you.
Not aware of any, no idea.
Cool, thank you.
And Brent had asked, constant C is a target to match without knowing what the data is. Favorite concept, social overlays. Do you want to talk a little bit about social overlays?
Oh, those two kind of, I guess the social overlay is kind of utilizing semantic information to try to cluster information. So if you have a semantic relationship, I know there's different, I sort of forget, but there's two different papers that I remember. There's one thing called Inga, and there's another thing kind of called Tribler. There's many more, but those are the ones I've read about. Tribler kind of uses these taste buddies, basically. So if your kind of friends like something, then maybe you like something too. Kind of a social recommendation. Inga was more of a protocol. I'd have to review that paper, but that's yeah. My brain again. My brain's kind of running slowly now. So, but I'll get back to you.
Yeah, no worries. If you happen to have links to those, if you want to drop them in the chat, we can make sure that they're attached to the notes after as well. But yeah, exactly. Like you need to have some mechanism for determining what's popular. And so you could do that with at the level of individual human beings. With this approach, it basically assumes that you're in a sort of randomly connected network. They try to overlay this on top of there's ADHD. We don't really care how it works underneath, and you can stick this on top, which is kind of a nice property, right? You can just slot it in on top. I found it interesting that they picked pastry specifically in the experimental section, the empirical section. It was 2004. Maybe it was less of a, less clear which DHG was going to win. Kademlia seems to be the default choice these days. So I'd be curious to see how see those experiments against Kademlia. But yeah, also constant C. This is more just like a style thing. But I found when I did my first, because I usually do like a quick high level read, and then I go through and I actually read everything sort of like in detail. When they initially introduce this constant factor, and they immediately jump to fractional. So they start with 1, and then they jump to fractional C. And so I assumed that was how likely it was to be on any particular node, where 1 would be on every node. It's actually the opposite. 0 is this is on absolutely every node. We've replicated this everywhere. Because it's the number of hops, average number of hops away required. Yeah, the other thing in the experiment is their network was not very large. It was, I think, 1024 nodes, something like this. It was basically tiny by today's standards in an open network. The DNS benchmarking suite was a little bit bigger, but again, these are not, I can't remember exactly where it is now, but yeah, somewhere. These aren't huge. Anyone have other thoughts on the paper? or should we give everybody 15 minutes back? Oh, all right, cool. Well, thanks everyone. This is obviously kicking things back off again. As you could probably tell earlier, pretty excited about next month's topic. I'd really consider doing it for this month. But again, wanted to give some other teams time to experiment with it and also just get the ball rolling again. It takes time for people to hear that this thing's going, unless I decide to email everybody, which I'm trying to ideally avoid. And if there's papers anybody wants to read, drop me a line. Zishan let me know the thing that we currently have listed for July. He ran a session last July on that exact paper. I was on vacation that month, so I didn't realize that. Irony. So we have to pick a new paper for July. Typically in summers, we pick something more on the practical end or lighter, just because people are on vacation. So submit anything you want to talk about. And other than that, see you all next month for a practical rateless set reconciliation. Oh, sorry, practical rateless invertible Bloom IBLT. Well, practical rateless Bloom filters, basically. Okay, see you.